on something extraordinary. Extraordinary and disturbing, that is. You recall what you said in New Delhi about how polar melting might disrupt the North Atlantic current?
Yes.
Well, I think it's happening.
What do you mean?
If you look at the linear trends from 1901 to 2013, you can see that practically every part of the planet has warmed, but there is one big exception, and that is exactly the area to the south of Iceland, which has shown a cooling. Luckily, maybe for you, where it's already very cold, it's not above the land in Iceland. The land temperatures have also warmed in Iceland, but not far away to the south of it, we have this cold patch in the North Atlantic. Now, that tells us something, because this region is exactly in the area where this ocean circulation in the Atlantic is dumping a lot of heat. It brings warm water up to that region, gives off the heat to the atmosphere. That cold water then becomes dense enough to sink down and return at depth to the South Atlantic and join this overall large-scale circulation of the global ocean.
What about the North Atlantic current?
What about it?
The current depends upon a delicate balance of salt and fresh water.
We all know that.
Yes, but no one has taken into account how much fresh water has been dumped into the ocean because of melting polar ice. I think we've hit a critical desalinization point.
The recent 2017 assessment, Abrupt Cooling over the North Atlantic, evaluated the risk of future abrupt subpolar Gaia cooling in the North Atlantic based on 40 climate models. The North Atlantic subpolar Gaia consists of the North Atlantic current and its equator side, the Norwegian current that carries relatively warm water along the coast of Norway, responsible for warmer European weather. Along the east coast of Greenland, the southward flowing cold East Greenland current, and the southward flow that continues off the coast of Canada is called the Labrador current. Part of this region experienced a rapid cooling around 1970, dubbed the Great Salinity Event, raising a debate over its potential reoccurrence. The authors find that continued CO2 emissions provoke abrupt nonlinear shifts in the dynamics of the subpolar Gaia, the latter being characterized by a permanent collapse of the local heat transport, convection, within the water currents. 14% of the modeled climate scenarios collapse the subpolar Gaia currents, leading to abrupt cooling of a few degrees within 10 years, directly impacting North American and European climates. While deep water convection and the Atlantic meridional overturning circulation AMOC are strictly connected, abrupt shifts in subpolar Gaia convection may not necessarily imply similar shifts in the AMOC. Because deep convection in the Greenland, Iceland, Norwegian Sea and in the Labrador-Imminger Sea, as well as the overflows from Denmark Strait and the Scotland-Faroe Channel, are all integral parts of the AMOC, deep water formation system. A collapse in one part of the system may occur without an equally abrupt response elsewhere in AMOC. This supports the distinction between two separated climatic tipping points for the North Atlantic abrupt cooling, namely one associated with a local subpolar convection collapse and one associated with a large-scale AMOC disruption. 31 models do not show any kind of abrupt cooling. 7 models abrupt subpolar Gaia collapse, 3 of those below a 2-degree global temperature rise, and 2 models simulate a collapse of the AMOC before the year 2100. However, the researchers also identified that many models lack in regards to how they project stratification. Also, in subpolar Gaia convection collapse weakens AMOC, the latter does not collapse but experiences a relatively limited and linear reduction. Subpolar Gaia convection collapse creates an atmospheric warming hole over parts of the North Atlantic, strongly influencing the temperature response over highly populated areas such as the eastern North American coast and Western Europe. The altered hemispheric temperature gradient also affects the precipitation patterns by shifting the position of the intertropical convergence zone in line with previous findings. In addition to the potential existence of a tipping point for an AMOC shutdown, the authors state, "We argue that a separate tipping point involving a collapse of subpolar Gaia convection also exists. Both AMOC disruption and SPG convection collapse are possible responses to the ongoing global warming trend and changes in the hydrological cycle that are freshening the northern North Atlantic. Our results highlight that in CMIP5 models, the occurrence of North Atlantic abrupt cooling due to an subpolar Gaia convection collapse is almost 4 times more likely than the occurrence of a North Atlantic abrupt cooling due to an AMOC disruption. Furthermore, when considering only the most realistic models in simulating the present-day subpolar Gaia stratification, the chance of a North Atlantic abrupt cooling in the coming century is close to 50%, while the chance of a complete AMOC collapse is very low. A final issue concerns the climate impact that a convection collapse in the subpolar Gaia has on the surrounding regions. The repercussions of such an event on temperature and precipitation represents an important hazard for many economic sectors, notably for the agriculture industry as well as for water resources and energy management. The assessment concludes that for the UK the chance of cooling as outlined is actually almost as large as the chance of a continuous warming trend. The authors stress the need to consider the potential risks associated with a subpolar Gaia convection collapse when developing future strategies of adaptation to climate change, as well as when searching for possible early warning signals of abrupt climate change in the North Atlantic.
And it's less certain how soon the North Atlantic will begin to cool. In fact, it's the last few years it has cooled, but we don't know if that's an oscillation or if that's really the beginning of the effect of the fresh water coming off of Greenland. But that, if we let that happen, that the fresh water become at a rate that's big enough to shut down the North Atlantic Deepwater Formation, the way Wally Broker hypothesized decades ago, then all hell breaks loose. Because you're cooling the northern latitudes while the tropical latitudes are continuing to get warmer because of the greenhouse gases. And that increased temperature gradient drives much stronger storms.
Now, to finish off, I want to look at some of, at least very briefly, some of the consequences that such a weakening of the overturning could have. One of the consequences is on sea level. Climate models predict that if the Atlantic meridional overturning circulation slows down, then the sea level on the US coast will go up, whereas basically on the left of the Gulf Stream it goes up. On the right-hand side it goes down, as you can see in this diagram. So that is a pattern that would be superimposed on the total global sea level rise here, and it would lead to a disproportionate rise on the US coast, maybe 20, 30 centimeters extra there on top of the global average rise for people living there in that region. Another consequence, of course, is the effect on the weather, and we are really only beginning to understand this with reasonably high-resolution models. Here is a publication by British colleagues that shows the effect of a decline of the overturning circulation on the storm tracks, and they predict with their model that it would significantly strengthen the storm track hitting into Britain and across the North Sea into Holland and Germany.